This is Team 16's project on League of Legends game production by Sean, Alex, and Ryan. League of Legends is a multiplayer online battle arena in which two opposing teams, blue and red, compete to destroy the enemy's nexus. The goal of our project was to determine if the 10 minutes of the gameplay is enough to determine the outcome of the game.
So for the methods for our machine learning project, our dataset was a series of statistics for about the first 10 minutes of diamond level gameplay from the Riot API. It describes almost 10,000 games and has 40 features, the most important of which is blue wins, which is a binary feature, which is 1 if the blue team wins, and it's 0 if the red team wins, and this is the label we are going to try to predict in this project. The rest of the features are simply their data about what happened within the game. So for example, the number of wards the blue team placed, same for the red team, and the amount of gold that each team got for themselves. The only exception would be the game ID, which is just a feature that the Riot API uses to identify each game individually, which is not something that's going to be useful for us since we're only interested in things that happen within the game. As for our feature reduction, we ended up reducing the dimensionality of our data by performing PCA on it. And as you can see over here on the right, we have a graph of the proportion of retained variance per principal component. And the first principal component is clearly the most important at 85% of the variance of the entire data set. So as you can see here, if we use the first 4 principal components of this data set, that'll actually end up being 99.99% of the variance. So this will reduce the computational complexity of our supervised learning techniques accordingly. Moving on, we used a 70% ratio for our training data and a 30% ratio of our total data for our testing data. And we used 3 types of supervised learning: regression, random forests, and neural networks. So for our results for regression, first of all, we start with logistic regression, and we ended up with a root mean square error of around 0.53 and an accuracy of around 72%. However, when we use logistic regression on the reduced data, our root mean square actually increased slightly to about 0.5333, and our accuracy decreased by about 0.75% to around 71.5%. And as you can see on the right, we have a graph of the accuracy of our logistic regression based on the number of principal components to be included within the regression. And as you can see, we have our 4 principal components over here at about 71.5%, and we have a general upward trend along with the occasional spikes due to fluctuations in the data, a general upward trend in accuracy because clearly as you use more principal components of the data, you'll get a higher accuracy overall. Similarly, with our ridge regression, we actually have some hyperparameters to tune in this case, including alpha, the regularization strength. So we use cross-validation built into the sklearn toolkit to find the best alpha in this case. We had a root mean square error of about 0.525 and an accuracy of about 72.46% on the raw data, and an alpha of 100 for the raw data. But when we use the reduced data set, we ended up with a slightly higher root mean square error of about 0.53, an accuracy of about 71.66, so about 1% lower, and a higher, much higher alpha of around 10,000. And over here, as you can see, generally we have an upward trend in accuracy, the more principal components that we include within the regression.
Next, we used random forests using Guinea impurity for splitting nodes into decision trees. Without feature reduction on the dataset, using 4-fold cross-validation, the resulting trained random forest had tuned hyperparameters listed here. The prediction accuracy was 72.53%. After applying PCA feature reduction on the dataset, using 4-fold cross-validation, the resulting trained random forest had tuned hyperparameters listed here. The prediction accuracy was 72.37%, only 0.16% less than without feature reduction.
For our neural network model, we had 38 ReLU nodes on the first layer and 19 on the second layer, and 1 sigmoid node on the output layer. We ran about 1,000 iterations, and we were able to achieve about 74.6% accuracy.
For regression, the accuracy of both logistic and ridge only went down by around 0.75% when using PCA. Although this difference is not negligible, it is still very small and most likely worth the decrease in computational complexity. The same could be said about the random forest, which saw an accuracy decrease of only 0.16% when using PCA. Each of the 3 methods gives similar accuracy results as can be seen in the graph. This is likely due to the limitations posed by the dataset itself. It simply does not have enough important describing features about the game. This is supported by the fact that only 4 principal components are needed to retain 99.99% variance in the dataset. However, this is still a much better result than the 50% accuracy that can be achieved by randomly selecting a team to win.
We believe that we were not able to achieve an accuracy beyond 80% due to limited information in the dataset. There are a lot more determining factors, such as champion picks and player-specific attributes, such as win rate and average creep score. In order to achieve a better performance, we definitely need a lot more data than just what is available from Riot's API.